Hi everyone, and welcome to the first of two videos go through some past exam questions on rates of reaction and the Boltzmann distribution. This video is going to have a few questions on rates of reaction, and then the second video is going to be all about the Boltzmann distribution. Okay. Right, let's have a look. These questions here says, right, we've got hydrogen peroxide, decomposes to make oxygen and water. It can be made faster by increasing the concentration of the hydrogen peroxide, adding a small amount of a manganese 4 oxide catalyst, or heating the solution to 60 degrees. Construct an equation for the decomposition of hydrogen peroxide. Okay, so it's going to be hydrogen peroxide is H2O2, and then it says up here, look, it decomposes to produce oxygen and water. So it's going to make oxygen O2, and it's going to make H2O. Then it's just a case of balancing it. I've got 2 hydrogens and 2 hydrogens, so that's fine. But I've got 3 oxygens here, and I've only got 2 there. So we need more oxygens on this side, right? So let's put a 2 here to start with. That then gives me 4 oxygens, but it's also messed up the hydrogens. They're not balanced now. So if I put a 2 there in front, I've got 4 hydrogens, so I'm going to need to put 2 here. So I've got 4 hydrogens here as well now. So that's good. But I've got 4 oxygens here overall. I've got 2 there and 2 there, so that is balanced. Okay. And then basically it's going to get us to talk about these things here. So explain why increasing the concentration of the hydrogen peroxide increases the rate of decomposition. So we need to explain what increasing the concentration actually means. Okay. So we can say a higher concentration means that there will be more molecules, means that there will be more H2O2 molecules per unit volume. Or you could say the same, more molecules in the same volume. Okay, that's what concentration means. If you think about the units, concentration is in units of moles per decimeter cubed. So moles is counting how many molecules you've got, and decimeters cubed is the volume, isn't it? So it's number of molecules in a certain volume. Okay, it's really important that you include this part. You can't just say there are more molecules. Okay, there's more molecules in the same volume, or more molecules per unit volume. Okay, and that phrase just means for every unit of volume. So it's more molecules per decimeter cubed or something. Why does that mean there's going to be a higher rate of reaction? Because if there are more molecules per unit volume, then there's going to be a higher frequency of collisions, right? The molecules are more likely to collide with each other because there are just more of them in that same volume. Be more H2O2 molecules per unit volume and a higher frequency of collisions. And again, it's important to use that phrasing. So in the same way as that it's, you must say per unit volume or in the same volume, or you must mention the volume in some way. Using the phrase higher frequency is the best way to make sure you get a mark. It would not be sufficient to say there are more collisions. Okay, that's actually not correct. It's not that there are more collisions. If we're talking about the rate of the reaction, it's the time it takes for those collisions to happen. Okay, the frequency increases. I'm getting more collisions per second. Okay, so it's about the fact that that number of collisions is taking less time. Okay, so that's why you need to include something about the frequency. Okay, explain how the catalyst can increase the rate of decomposition. So this is just explaining what a catalyst does. So this is just one you need to learn, really. There's, again, a certain wording for this that they do allow you a bit of leeway on, but it's best if you can word it exactly how they'll want you to write it. So a catalyst provides an alternative pathway for the reaction. Or you could say a different mechanism. An alternative pathway for the reaction. So it allows the reaction to happen in a different way, essentially. Pathway for the reaction with a lower activation energy. Remember, the activation energy is the minimum amount of energy needed to start the reaction. So the catalyst is saying, you can do this reaction with less energy. Okay, and actually that would be sufficient to get you the 2 marks here. That's all you need to write. But but you could add a bit of extra detail. You know, if it was a 3-mark question, let's say, how would we get the 3rd mark? So you could then say, this means more molecules have energy greater than the activation energy. You know, if you're saying the activation energy is now lowered, right, the requirement for energy is lower, well, then more of the molecules are going to be able to meet that requirement. And that's why you get a faster reaction. More molecules have energy greater than the activation energy. Leading to a higher rate of reaction. Okay. Right, and the last bit on this page, describe and explain the effect of decreasing the pressure on the rate of reaction. Okay, so if we've decreased the pressure, first thing is, well, what is the effect on the rate of reaction? Make sure you actually say that. Some people go straight into the explanation and actually miss out the obvious part. Okay, so decreasing the pressure decreases the rate of reaction. That's the first thing. You definitely want to make sure you've said that. Because, and then pressure is very, very similar to what we talked about with concentration. It's about how many particles you've got in a certain volume. Okay, if you've decreased the pressure, then essentially what you've done is just increased the volume. So you've got the same number of particles, but there's now a bigger volume for them to move around in. Okay, so we can say there are fewer particles or fewer molecules, that would be fine. Fewer particles per unit volume. In a certain volume, there's going to be less particles because there's a bigger volume for those particles to spread out in, so they're spreading out more. Fewer particles per unit volume, so the frequency of collisions decreases. Again, it's that frequency of collisions phrase that you want to use. Okay. Right, the next question is another one about catalysts, and we need to be able to represent the effects of a catalyst on one of these enthalpy diagrams. So let's just see, what does it say here? Catalysts can be used to change the rate of chemical reactions, fine. Zinc and sulfuric acid react together to form a solution of zinc sulfate and hydrogen gas. Okay, the reaction is exothermic. The rate of reaction increases when a catalyst is added. Complete the enthalpy profile diagram for this reaction using the formula of the reactants and the products. Label the activation energies without a catalyst and with a catalyst, and label the enthalpy change of reaction. Okay, there's quite a lot of information here then. So the first thing that's really important here is this, where it's saying the reaction is exothermic. Okay, so we need to draw an enthalpy level diagram for an exothermic reaction. Okay, so what that means is that exothermic is going to release energy. So it means that the reactants are going to start off with relatively high energy, and then the products are going to have less energy, because energy is going to be released during the reaction. Okay, and so we can put on the enthalpy change is going to be that gap there. So we've labelled the enthalpy change of reaction, that's done. Complete the enthalpy profile diagram using the formula of the reactants and the products. Okay, so we need to actually write the formulas on. So this was zinc and sulfuric acid. So we've got zinc and sulfuric acid as the reactants, and it's making zinc sulfate and hydrogen as the products. It doesn't say anything about state symbols, does it? No. Okay, make sure you read that kind of thing carefully. A lot of people just would write reactants or products here. It specifically says using the formula. So you will lose a mark if you haven't done that. Okay. Right, and I think this is always a good trick to do. If you've got something with lots of bullet points in, just tick them off when you've done them. So we've put the reactants and the products on with the formulas. We've put the enthalpy change of reaction. We need to now show the activation energies. So the activation energy means you have to put a bit of energy in to start the reaction off. So that means that my enthalpy profile goes up a bit first before it comes down. Okay. And so this is going to be my activation energy without a catalyst. That's the energy I've had to put in there. If I do use a catalyst, then that's going to reduce the activation energy, right? So it means it's going to be lower. Okay. The activation energy is always from the reactants right up to the top. Okay. So I'm going to draw a second curve with a lower activation energy, something like that. Okay, and I'm going to put my activation energy on as that gap, and it wants me to label that as EC. They will usually let you get away with using slightly different labels as long as it's clear what you mean, but they have told you here what they want you to label it as, so just read the question and use those labels. That's the easiest thing. And then you're guaranteed to get it right. Okay, so there's our diagram. Then it says here, the chemical industry uses catalysts for many of its reactions. State an example of a catalyst used by the chemical industry and write the equation for the reaction that's catalyzed. So, I mean, there's any number of different reactions you could choose here. It's just asking you for anything that involves a catalyst. But one common one that you'll have seen before is in the Haber process. We've seen that at GCSE probably. So the Haber process is nitrogen reacting with hydrogen to make ammonia. It's a reversible reaction. So it's often used as an example of a reversible reaction at GCSE level. And the catalyst that you use for the Haber process is iron. But there's a whole bunch of other things you could use there. There's a lot of organic reactions that have acid as a catalyst, for example. You could have nickel as a catalyst for hydrogenating alkenes. There's I could be here all day listing reactions that involve catalysts. So as long as there's something sensible you can come up with. But there's a good example. Right, and then finally, this kind of question actually comes up quite a bit. Things to do with catalysts being sustainable. So 2 ways the use of catalysts helps chemical companies make their processes more sustainable and less harmful to the environment. So this actually comes up quite a bit, and it's not just it lowers the activation energy, it provides an alternative pathway. That's explaining how a catalyst works. This has got to be linked with stuff to do with the environment, making it sustainable. So there's a few things you could say here. So if we use a catalyst, it does lower the energy, lowers the activation energy. The benefit of that is that we don't need to heat the reaction up as much. Yeah, because we're saying it doesn't need as much energy to get started, so why do we need to heat it? So it allows the reaction to be performed at lower temperatures. Why is that? What's that got to do with the environment? Well, how would we be heating it up? You'd be heating it up by burning some kind of fuel, usually. Okay, so it allows the reaction to be performed at lower temperatures, so less fossil fuels are burned. And less CO2 is produced. So that's going to help it to be more sustainable. We're going to be causing less pollution. Obviously, CO2 is a greenhouse gas. You wouldn't need to go into that there. If you're talking about CO2 being produced, that would be absolutely fine. And that would probably be enough for us to get the 2 marks, because we've kind of said a few things there. We've got lower temperatures, less fossil fuels, less CO2. So that's pretty good. The other thing you could talk about is just the fact that catalysts would just make your reaction much more efficient. They're going to create less waste. So catalysts mean less waste will be produced. Obviously, the good thing about catalyst is you can reuse it lots of times. It doesn't get used up in the reaction. So then there's not as much waste there. So that's a benefit as well.